Well, hello, I'm Andrew Whitechapel, and I'm going to talk to you about resource management, primarily memory and CPU, and how it affects your app and how your app can take advantage of memory and CPU policies. So first we'll look at why you should even pay any attention to this at all. Why does it matter to you, and why do you actually have to do anything about it? And then we'll look at all of the things that policy covers. It mainly covers memory and CPU, or memory and CPU are the two most critical things that it covers, but it covers lots of other things as well. And we'll look at the rationale behind this, why the system does this, and what it's trying to do in policing these resources. And we'll look at the structure of how it's implemented so that you can see how it's trying to achieve the goals of resource policy. And policy does vary. There's a single resource manager on the system across all of Windows 10. And there's a single policy, but the policy values change according to the SKU and according to the device. And they can also change dynamically according to the conditions that arise at runtime. And we'll look at some code, because this isn't just something that's imposed externally on your app. It's something that your app can take advantage of. Or not. You can take part in this, and you can cooperate, and you can use it to your advantage, or you can completely ignore it, which tends to be the less good choice. And we'll look at the code options that you have in the API. So why should your app pay any attention to this? Well, we're making some assumptions here. My first assumption is that you want to target a sensible range of different devices. So it's possible that you actually want to target all possible Windows 10 devices across all possible SKUs, so across mobile and desktop and IoT and Xbox and HoloLens, and every single device within those SKUs. That's somewhat unlikely, although it's perfectly possible for some types of apps. But for most apps, you'll probably be targeting a subset of that. You might target like all of desktop, every single desktop device that runs Windows 10. Or it might be a combination, all of desktop and all of mobile, or desktop plus Xbox, or some permutation. But the point is that this is a very wide range of devices. Even within one SKU, it's a wide range of devices. You can imagine a desktop PC that isn't a single thing. It ranges from a PC that might have only 1 gig of physical RAM and a tiny page file and a really slow disk and a low resolution screen, all the way up to something that has maybe 128 gig of physical RAM and a huge fast disk with lots of page file that grows dynamically and multiple high-res screens. And so there's a big range, even within one SKU. And if you go across SKUs, the range gets even bigger. So the assumption is that you want to target more than just one single device, and therefore you're going to have to accommodate different device configurations, different memory, different screen resolution, different networking capabilities, different keyboard, mouse, hardware, and so on. And it's not just something that you plan up front for a particular device, and once it's installed, that's it, because things change at runtime as well. So even though you say, well, I'm targeting this range of devices have a minimum memory requirement of X and a minimum screen resolution of Y, and it must have a mouse, and it must have Wi-Fi, and it must have whatever. But these things can change, even within the things that you consider important to your app. And the changes fall into 3 broad buckets, what I'm calling hardware changes. So you install your app on a device that's got 2 gig of physical RAM, and then the user installs some more memory. Or they had more memory and they take some out, or they install an additional hard disk or an external screen, or so those things can change, and you would want to take advantage of more memory. And equally, you would want to adjust yourself in the face of memory going away suddenly. You wouldn't want to just fall over and stop working. And then the second bucket I'm calling connectivity, because it includes things like network connectivity and the strength of the connection and the speed of the connection. but also things like cellular data and am I in a roaming zone? And then state changes, and these are changes that are particular to the Windows app platform, where things can change depending on what you're doing. So, for example, if you're a foreground app with UI that the user's interacting with actively in the foreground, then resource policy says that you'll get a certain amount of memory, or up to a certain amount of memory. But if the user switches away and navigates to some other app, then the previous app is no longer the foreground app. It's no longer being interacted with. And so its resource grants change. It might get less memory, it might get less CPU, it might not have the same access to critical sensors on the device that it would have otherwise. So things can change at runtime according to the state of the app. And then the user might switch back again, and your previous app now comes back into the foreground, and then it gets, again, the change might go in the other direction. It might get more memory, it might get more CPU. So your app, it pays you to pay attention to the conditions that you find on the device and to continue to pay attention as these conditions change. And there are a couple of fairly obvious things as well that are consequences of either paying attention or not paying attention. One is the battery, the wall of shame. So the system reports in the UI to the user so that they can see the energy consumption of each app, and particularly when apps go above certain critical thresholds, and we consider them to be very energy consumptive apps, very energy intensive apps. So generally, you would prefer your app not to show up on that list at all, or at least if it does show up, to show up with a very small bar saying it's not using very much energy. Because if it does show up on that list a lot and it uses a lot of energy, there's the risk that the user will turn off your app or uninstall it, because they may have a preference for battery lifetime or reduced energy consumption over whatever features your app is providing. And equally, you would want to pay attention so that you don't do one of the two extremes. You don't crash. So, for example, if you're making excessive memory allocations, you will eventually get an out-of-memory exception. If you handle that, if it's propagated to you and you can handle that, then you can continue on. If you don't, if you just ignore it, then your app will be terminated. And from the user's perspective, that looks like an app crash. And at the other end of the flip side of that bad behavior is where you don't crash, but you're consuming so much in terms of resources, so much memory, so much CPU, so much network bandwidth or disk I/O, that the rest of the system slows down. And again, the user will see that eventually they'll figure out that your app is badly behaved, and they will, there is a risk that they will uninstall it. So what you want to do is to take full advantage of the system, use all the features that it has available to you without negatively affecting the system and without negatively affecting the overall user experience. So the system polices resource constraints. On most devices, resources are, well, on all devices, resources are finite. Even if you consider a huge desktop with 128 gig of RAM and a massive hard disk, there's still a limit to how much is actually available. And the user can keep on installing additional physical RAM up to a point, but there's still going to be a limit somewhere. And certainly at the bottom end of the scale, the constraints are very severe. So if you think of a 512 meg mobile device, it's got very little memory to start with. It's got a very small, very slow page file typically. And then there's everything in between. So we have to manage these finite resources in the face of multiple apps, multiple background tasks wanting to run concurrently. And so there's obviously resource contention. And what we try to do is to maintain a balance in the user experience so that we don't grant full resources to any one app or any one task. It's not a single tasking system. So even though the user is interacting with some app in the foreground, we don't give that foreground app everything on the system, because that would mean that other things that the user is expecting won't be happening. So they expect to be able to receive incoming calls, for instance, or Skype VoIP calls. They expect their email to sync in the background. If they kick off a download or an upload, they expect that to continue and to make progress in the background, even though they might be doing something else in the foreground. So we try to balance all of the things that could be happening, and we give more resources to some things in some situations and less resources to other things in other situations, and things change. So it depends on the type of task that it is and how it fits into the balance of the user experience, what it's actually doing for the user, whether the user is aware of it and is interacting with it directly, or is simply aware of it but is not necessarily directly interacting with it. And then things at the other end of the scale which they know happen sometimes, but they're not quite sure when, and they never know when, and they don't see it happening. And in balancing all of these different competing resource requirements, we want to achieve predictability so that the user can expect things to happen, even though they're not directly interacting with them, and so that the app knows what to expect. We provide enough API surface so that the app can actually figure out what's going on, can respond to changes, can get notifications when things that affect it change, and can react accordingly, instead of just falling over unexpectedly. So I've mentioned already that the main things that policy covers is memory and CPU. But we also police task lifetime, so different types of tasks get to run for a different length of time. And we also police access to certain device sensors like the microphone and the camera and the speech synthesis and so on. And there are a few other things that we police as well. And it's all part of providing this holistic experience where we balance the competing requirements of different task types with a view to maintaining the user's expectations and meeting the user's expectations. So memory, first of all, this is just an example. I mean, don't pay too much attention to the specific numbers. And you can imagine, obviously, since we cover multiple SKUs and all of the devices within that SKU, the matrix of possible values is huge. So don't worry too much about the specific values. Just look at the example math that's going on here. If we take the first column, the 512 meg phone example, I'll just follow it down so you can see what the math is that we're using. This is obviously very simplified, but we look at the device. It starts with 512 meg of physical RAM. We look at the paging level on the device. Now on this device, it's going to support a 256 meg page file, but typically on these devices, the storage device is slow, and so we can't use all of the page file. We can generally use up to about 80% or thereabouts before the system is thrashing so badly that performance is actually worse than if we used less of the page file. So we assume around about 80% of that 256 to give us 200. We add that up, and that's our base. Those are like the hard physical constraints. We have no more resource than that. That's our finite resources in memory. And then we look at the things which are pretty much guaranteed reservations. So the board support package, if there is one, the operating system itself, the drivers, the system services. All of these things are effectively unpoliced, but they take up memory. So we allow for those. Then we allow for some things that we do police, but we have to pretty much guarantee. So if the OEM or the mobile operator has deployed a service agent on the device, then that has to run. If you've got VoIP on the device, then that has to run. You have to be able to take an incoming call. And so the task that's managing that incoming call has to run, because otherwise, if it's not running, by the time we start it up, the other end, the server will have dropped the call because the delay is too long. So we have to keep this thing running. VPN, again, if you have VPN, then everything has to go through VPN, and therefore that has to be running. So there's some critical carve-outs that subtract from the available memory. So we take the physical and the page file, we subtract all the guaranteed carve-outs, and what we have left is what we use for everything else, for the foreground app, for all of the background tasks, for the backstack, for things like task completion and so on. And you can see in this example, and remember I said don't worry too much about the specific numbers, but this is a fairly typical example on a 512 meg mobile device, that we had 712 to start with, we've carved out 523, that leaves us with 189. And we've given 185 to the foreground app, which leaves us 4 meg, if we're lucky, for apps in the backstack, apps doing task completion in the background, any background tasks of any kind, apart from the critical ones, which isn't a lot. So you would think that this is not a sustainable matrix of memory usage. And it isn't, generally, but then also generally this is worst case scenario. This is if everything on this list was using the maximum that we know it normally uses all the time. Now some of these things we have pretty good numbers on, like the OS and the drivers and services. Those are policed prior to ship, so we know how big those things are, and we know how much they spike and when they spike and under what conditions. So we've got a pretty good handle on the size of those things. We've also got a pretty good handle on the size of the critical managed services, like the service agents and VoIP and VPN. And those do have caps imposed on them, so we know they can't go above their caps. And they typically actually approach their caps most of the time. So what we're carving out for them is a very tight fit to what they're actually using most of the time. It's the things at the bottom that we have a little more leeway with. We give the foreground app 185 meg as a cap, but most apps don't use that. Most apps use half of that most of the time. So it's really a percentages game. We assume that some high percentage of the time the user experience will be protected, because most of the time the app that they're running is not going to be consuming up to its maximum cap, and therefore there will be something left over for the less critical background tasks that are running in the background. And typically they will have a lot more than 4 meg most of the time. And then if you look at the other examples, at 1 gig tablet, things free up a little. We have a little more memory to play with after everything has been carved out and reserved. But then again, the foreground app cap is bigger, and this is partly it's almost a circular calculation. But we look at telemetry data on apps that have been deployed and see how much they actually consume in the wild to figure out what would be a reasonable cap for a foreground app, and what would be a reasonable cap for every different task type. And then if you look at the last column, the 2 gig desktop, we seem to have lots of extra memory floating around despite a huge cap on the foreground app. But don't forget that on this sort of device, the user is going to expect to be running multiple foreground apps at the same time. So on a small mobile, they won't. They know that they switch from one to the next, and there may be the appearance, the perception of multiple apps running at the same time, but typically there aren't, whereas on a desktop, typically there are. So we have to balance all of those different user expectations across different devices with the physical characteristics of those devices. So memory is the main thing, but we also police CPU usage and lifetime and a few other things I mentioned. So here's again just a few simple examples. A default background task that's not doing anything very much. It might be updating a live tile, perhaps. 16 meg memory cap. It only gets to run for 30 seconds at a time. So it has to complete all its work in 30 seconds, which if you think in CPU terms is an awfully long time. This is 30 seconds wall clock at a rate of 10% CPU usage. So it can do an awful lot of work in that time. And typically there'll be more than one running at the same time. And other things we police, like is it blocked in battery saver? So if the user's turned on the battery saver feature, they can enable or disable most background task types on a per app basis. Whereas some things like VoIP and the foreground app, these things are not blockable. If the battery saver is enabled, these things continue to run. And also the lifetime cap for these things is infinite. There is no cap. So a foreground app can run forever. For as long as the user wants it to run, the foreground app can run. Unlike most background task types, which have some kind of limit on them. And this is just a small set of the different task types on one particular device configuration. You can imagine the matrix of different task types with their different memory caps, their different lifetime, their different CPU quotas, and other constraints. The matrix is very large. Another aspect to how we police policy is task priority. So we look at all the different scenarios in a situation where there is no contention, where there's just a few things running, or maybe only one thing running, and there's plenty of resources. Then the priorities are irrelevant. They only come into play when there is contention. So if we have multiple things running at the same time, we have a foreground app, we have maybe background audio playing, maybe there's a VPN running and a couple of other background tasks, and Bluetooth or sensor task running. And then we get a request to activate another task of some kind. What we do is we look at that task and we look at the priority that's been assigned to that task. And we look at the priorities of everything that's running. So if we don't have the resources, so typically the memory, if we don't have the memory for this new activation, we look at everything that's running. And if we see things running that are of lower priority than the incoming task type, then we will terminate those things of lower priority in order to meet the requirements of the incoming activation request. And we'll terminate just enough of them to free up just enough resources so that this new thing can run. And this is why there's kind of two categories. There's all of the important stuff at the top, which also tend to have the sort of permanent memory carve-outs, but these things are guaranteed. So those things won't get terminated, ever. But things at the bottom will, things with any lower priority than 2, and the number again is arbitrary, and this is a subset again, so there's a lot more priorities. But we'll terminate things that are not critical, so the opportunistic task types will be terminated if we need to for a higher priority incoming request. And if we get a request for an activation and there is nothing currently running that's of lower priority, then we bounce the request back to whoever asked us to launch this thing, which is typically the component in the shell or component in the foreground saying, please launch this thing. Or it could be the background task manager. And we say, well, we can't give you resources now. Do you want to wait? And it's up to the activator for this task type to decide whether it wants to wait or not. Some task types, it makes sense to wait. If it's a periodic background task that fires every 30 minutes and we ask it to wait for a few minutes till we get resources, that's probably fine, it can wait. If it's some supercritical thing that must be activated right now, like maybe even something of middling importance like a geofence trigger, if we don't respond to this within some period of time, if we can't activate the task within a reasonable period of time, then it's probably not useful anymore. So again, it's up to the different task type as to whether the request is queued and deferred until there are resources, or it's just dropped on the floor. And as a note here, I mentioned that some things change dynamically. So priority is actually one of the things that mostly doesn't change, but sometimes it does. So for example, background transfer. If you have a foreground app running and it kicks off a background transfer, the background transfer will run in the background, but because it's part of the foreground app experience, it will be given a higher priority so that it can complete sooner. If, on the other hand, it's running as part of a background operation, then it's given a much lower priority. So it depends on the context. And there are several tasks like this where their priority actually varies. Another thing I mentioned that policy controls is access to certain sensitive device resources like the microphone, the camera, speech synthesis and speech recognition. And most of these are privacy issues. So if you're running in the background, this is an example of a background agent, background audio agent. If you're running in the background, you typically are not allowed to use the microphone or the camera because there would be a privacy issue if you were recording sounds in the background or taking photos in the background, which the user wouldn't necessarily be aware of. I mean, they know when it's happening if it's in a foreground app, and that's their choice. But if it's running in the background, they don't necessarily know that the thing is happening at all, and so we wouldn't want you to be able to use critical resources like that without their knowledge. So these things are gated by the resource manager, and again, remember this can change depending on whether your app is in the foreground or the background. Okay, let's look at some code. We'll look at the code to use the protected resources is pretty straightforward, but there's a lot of different APIs for each of the different resource types. And then the memory manager and energy manager APIs are very similar to each other, deliberately so. And they provide enough information, enough finely grained information for you to make sensible choices, either during development as part of your own diagnostics, or as part of diagnostics out in the wild in production as part of your own telemetry, or just to react in a less finely grained way to changing conditions. Let's look at them. So here's some examples, and I've deliberately just put everything or a lot of things all on one slide here. This is examples of APIs that you would use to check whether you have access to a particular resource. And remember, these things can change. So at the top, there's an example of some events that you might want to listen to, like when the network status changes. So do I actually have any connectivity at all? And if so, what kind of connectivity? What speed have I got? The battery, the state of the battery, is it, do I have a battery? If I have a battery, what state of charge is it at? And is it charging or depleting? And then there's a whole range, and this is, again, is just a small subset of different classes that represent sensors, like the gyrometer and the accelerometer and the compass and the camera and various other things. You would typically get hold of the thing and then check to see if it's null, because it might be null either because there isn't one on the device, which you would obviously want to know, or because you don't have access to that thing at this particular point in time. In some cases, you might want to, even though you've got hold of the thing in the first place, you might want to continue to work with it surrounded by try-catches, because you might have got it while you were in the foreground and then you transition to the background and you continue to try and use this thing, but you won't be able to necessarily once you've gone to the background. So you should, even though you've got hold of it successfully in the foreground in the first place, you should check periodically and check if you get notifications to say things have changed. Battery, here's another example. Get the battery report. It could be that there is no battery, in which case we're not going to get any capacity, but if there is a battery, we might want to look at the capacity and see how much charge we have left. And then we can use that to decide whether or not we want to do some operation that we know is very energy intensive. Network connectivity. You can get the user's profile and you can check things like, are we roaming? How are we in relation to our data limit? Are we approaching the data? Are we over the data limit? And you would tune your behavior in accordance. You would not want to do things that are going to use more bandwidth if you're approaching or even if you're over the data limit. So all of these things, you just have to check whether you can get the thing in the first place, check when things change, listen for change notifications. don't just assume that you have access to any of these things. They may not even be physically present on the device. The memory APIs, we've had memory APIs in previous releases of Windows Phone. These have been brought forward and extended, so there's more things that you can get, more properties and methods on the API. This is the windows.system.memorymanager class. So there's some events. We'll tell you when your memory usage is increasing, and we'll tell you when it's decreased. So you can track that. You can see whether your memory is growing, and you can, each time you're told that it's growing, you can check to see what it is and see whether you want to do anything about it or not. See if you want to tune your behavior. You can find out what your cap is, the app memory usage limit. You can find out your current usage. Obviously, subtracting one from the other gives you the amount of headroom you have to play with. And you might want to do this over a period of time, particularly during development. You might want to track the memory consumption of certain operations and the memory trends to see if you're continually increasing, which suggests there might be a leak somewhere, perhaps. So there are some very simple properties you can access from the memory manager. There's also a method, getAppMemoryReport, which gives you even more detailed information. It breaks down the usage and the limit both relate to a combination of private plus shared commit. But you can get the private commit on its own if you want. The total commit usage is going to be the same as the app memory usage. The total commit limit is going to be the same as the app memory usage limit. But this, you can either, if you're only interested in those values, you can query those properties directly. If you want to get all of these things all at once, in an atomic way, where you know that this thing is taken, a snapshot is taken exactly the same time as this thing, then call the method. There are more. This isn't actually an exhaustive list of the methods and properties. There are a few more in here as well, but it's just to give you an example of the sorts of things that you can get, the sorts of information you can get. Some of them will be more useful during development to back up your memory profiling work that you're doing. Some of them will be directly useful at runtime in production. The Energy Manager has a similar pattern, it's a similar design. There's actually two. There's a background Energy Manager, which I'm illustrating here, and a foreground Energy Manager. So you use the background Energy Manager in a background task, and use the foreground Energy Manager in a foreground app. And again, we will give you notifications when your energy usage crosses certain interesting thresholds. And you can see there are hopefully meaningfully named values here, like your usage is a low. You're at low usage level. You're at near max acceptable. You're at max acceptable. So max acceptable is a level that we consider to be reasonable for a task under normal circumstances. So most tasks actually won't reach that level. They'll be just below that level most of the time. But you can go above that level. You know, assuming that all your other resources are still available to you, like memory and lifetime and CPU and so on, you could go above what we consider to be an acceptable level. It's a fairly arbitrary level of what most tasks do most of the time. But you can go above it, and we'll tell you when you've gone above it and you've crossed the next interesting threshold. And you can continue to go above it, but there comes a point where you're going to reach what we call the termination level. And when you're nearly at the termination level, this is your last chance, this is your last notification before we terminate you. It's very unlikely that most tasks are ever going to get to that level, because this is set at such a high level that you would have to be draining the battery at a very fast rate. But we put this in place so that if you are draining the battery at a very fast rate, you can mitigate your behavior. You can tone it down if you want to. And if you don't, then we'll terminate you. I should call out that only certain types of background task are terminated. The foreground energy manager doesn't have a termination level because we don't terminate the foreground app. You can use as much energy as you like in the foreground. Obviously, if you want to be a good citizen, it's still up to you to tune your behavior so that you don't use lots of energy if you can avoid it. But you're the foreground app, so we will allow you to consume as much as you like. Whereas in the background, and it will only be for long-running background tasks as well. Short-running tasks cannot reach the excessive levels. It's just not physically possible. But a long-running task could. So if it's doing something that's significantly degrading battery usage over a long period of time, then we will consider terminating it. But again, as I say, it's unlikely that most tasks will ever get to that level. And I mentioned before that policy varies. So it varies in multiple dimensions. It varies by SKU. So if you consider Windows 10 covers mobile, desktop, HoloLens, IoT, Xbox, the physical characteristics of the devices that support those SKUs are different. So mobile devices run from a 512 meg device with very small storage and low resolution screen up to a tablet that could have 16 gig of physical RAM. It could have a large, fast page file. It could have a much higher resolution screen. The desktop range overlaps that because desktops, in theory, you could have a desktop device that has 1 gig of physical, but you could also have a desktop device that has 128 or 256 gig of physical, and all the permutations in between of physical memory and page file size and speed of disk and screen resolution and so on. And then devices like HoloLens and Xbox kind of sit in the middle in the sense that there is no 1 gig HoloLens, there is no 1 gig Xbox, there's no 512 gig Xbox. So they come into the sort of middle of the range. And equally, there is no 256 gig Xbox. Down at the bottom, from my perspective, with my resource manager hat on, down at the bottom of the scale, all devices look pretty much the same to me. So a 1 gig phone and a 1 gig tablet and a 1 gig desktop device and a 1 gig IoT device, in terms of the available memory, the availability of page file and the performance of that page file, the screen resolution and so on, they look pretty much the same to me. So resource policy is almost identical down at that level across all SKUs. But then it starts to diverge. As you go up the scale, as you get more resources available and better resources available on bigger devices, then the policies diverge across the different SKUs. The key factor in deciding policy is the amount of available commit, which means physical plus page file. But we also look at the screen resolution, and we look at other things to decide what kind of device this is. The screen resolution is important because the higher the resolution, the more memory is tied up in graphics buffers, which are allocated on your behalf in your app. And so apps tend to, if you're running this exact same app on a device that has the exact same memory but has a different screen resolution, then the graphics memory usage will be different. So we have to factor that into our calculations. We also vary policy by app technology. So there's existing policy in place that has been in the past for Windows Phone and for Windows 8.0 and 8.1. And then there's policy for universal apps, so Windows 10 universal apps, and Win32 apps. So really, at a simple level, all of the pre-Windows 10 app types, so all of the Windows 8 X XAML types, all of the Silverlight types and XNA and native hybrids and so on that we had in Windows Phone before Windows 10, they have the same policy that they've always had. And this is an app compat issue. We don't change their policy. They stay as they were. So they get all the same behaviors as they had before. Universal apps have a different policy. In some cases, it's only very slightly different, and it's based on the old the old Windows Phone 8 policies, but extended and brought forward for the range of different SKUs. So the policies are different. So if you build a Windows 8 app and you build a Windows 10 app, universal app, they will have slightly different policy on most devices. It's only slightly different. In some cases it's not, in some cases it's the same. And then Win32, we don't police those at all, so there's no policy. Pre-Windows 10 desktop apps, so pre-Windows 10 immersive apps for Windows 8 and 8.1, they didn't have any memory caps, for example, so they continue not to have any memory caps. Just like Win32 apps, they do not have any memory caps. Because, again, we want to maintain app compat, so we don't break any of those things just because we have a new model. So policy varies across these different dimensions. And finally, what's the takeaway from this? Well, I hope I've given you enough information, and reading between the lines, hopefully you've got the message that there is a very, very large matrix of resource constraints, memory caps, CPU quotas, lifetime quotas, access to device resources, and so on. It's a very large matrix that varies across multiple dimensions, the device configuration, the SKU, and so on. If you want to target a reasonable set of different devices and different SKUs, you need to pay attention. You need to query the system, find out what you're actually running on. So am I running on a desktop with 128 gig, or am I running on a mobile device with 512, or am I running on an IoT device? So query the system, find out what's available to you, tune your behavior accordingly, and then also listen for change notifications. So when your memory cap changes, or the network connectivity changes, or your CPU quota changes, your energy consumption changes, listen for notifications, and again, act accordingly. Tune your behavior, throttle down your behavior or unthrottle it, depending on the notification. So in this way, you will be able to target the widest possible range in a way that's seamless to the user, that you will behave appropriately on each device without being horribly slow on one device and super fast on another device. You can tune your behavior, which might mean, tuning the feature set, but it might mean just tuning the resolution of your graphics images, or, there are all sorts of mitigations you can take once you've interrogated the system to find out what you're running on. Well, and thank you for watching.